of optical bistability in nonlinear resonators for digital light control between theory and technology. And our work, the general outline of my presentation will be as follows. First of all, I would like to give you an introduction to the framework of our research. Then I would like to highlight our theoretical contributions. And in the third part of the talk, I would like part of the intensity is transmitted, part of it is reflected. In order to do or to build an optical logic gate. Well, the theory of operation of such a device was proposed by Miller in 1981, and he presupposed that inside this cavity you had a forward and a backward beam. Another assumption that he made was that his waves were plane waves and that the amplitudes and the phases of these beams were slowly varying in space. He found that the structure could be described by two equations. The first equation is an area curve, the second equation a load line. The first equation gives the relation from the overall transmission and the effective irradiance inside the cavity. The second line, the second equation, gives you also the relation between the overall transmittance and the effective irradiance, but this time via the incident intensity. Solutions. And the first equation is given by the red curve here, it's the area curve. The second equation, the blue curve, is the load line. One is an unstable solution. If we translate that in terms of incident and transmitted irradiance, we find this kind of transfer characteristic which clearly shows a bistate, which clearly shows a hysteretic behavior. Now what can we do with the hysteretic behavior? That nonlinear fabric pair that we just described can function as an optical logic gate. No, I'm allowed to follow the process. Now, the further outline of my talk will be as follows. I will concentrate on the main results of the thesis. And a few years ago when we started this subject, the first thing we wanted to do, the first thing we had to do was to put the basic questions. Now, what are the basic questions? Miller, that, as I told you, brought forward the theory of operation of the nonlinear fabric pair. If we will base our extensions on that theory, the first thing we have to do is look whether it's correct. Second, since a lot of architectures and schemes make use of obliquely addressed nonlinear fabric pairs, a second question could be, can we extend Miller's approach that was brought forward for perpendicular incidents? Can we extend that approach towards oblique incidents? The third and important question is, can we analyze the impact of the different parameters on the behavior of the nonlinear fabric pair? Why should we do that? Well, if we want to improve the characteristics of the device, we want to know how or what the impact is of each and every parameter. A basic question concerning the dynamics of the nonlinear fabric pair is the following: a low to a high state, without changing the incident irradiance. In fact, this is a new switching mechanism, where applications are rather evident in case of for example, you can looking at oblique incidence makes your optical bistable characteristics angle sensitive and polarization sensitive. Angle sensitivity can lead to tuning of the nonlinear fabric pair, whereas polarization sensitivity can make a link between polarization and light level logic. It can also change the function of the device, and you can use it to characterize response times of nonlinear materials. A third question concerning the steady state operation is, what is the impact of the parameters on the behavior of the nonlinear fabric pair? And as we already said, the nonlinear fabric pair is described by two equations, two transcendental equations, the area curve and the working line. Now, if we want to know what is the impact of a certain parameter, for example, the angle of incidence, if we want to know what is that impact on the behavior of the nonlinear fabric pair, each time we have to solve these equations over again, and we have to plot the results on the same graphic. This gives a rather messy image, and this allows only to draw some qualitative results, to draw some qualitative conclusions. For example, here you can say that the bistable loop goes to higher irradiances and the loop becomes broader, but that's it. There is no quantitative conclusion that can be drawn here. If we want to get rid of that qualitative image, that qualitative picture, and we want to make it quantitative, the first thing we have to do is we have to characterize the bistable loop. And we can characterize the bistable loop by 2 points, the switching up and the switching down point. And these points, they can determine the whole bistable loop, and you can use them to define the contrast of the loop and the width of the loop. And the contrast and the width of this bistable loop are related to fan-out, bias power, and switching energy, some very important requirements that should be fulfilled if you want to use the device in an optical computer.